will be for molecules that have been part of chemistry we've been discussing lately. More on Nernst equation. Use, applications. Last time we talked about the Daniell cell, which is a name given to the zinc, hydrated zinc ion, hydrated copper ion, copper cell. Because a fellow named Daniell did a lot of investigations with that long ago, and in so doing established a lot of the fundamental considerations that are part and parcel of electrochemistry. Here again is this cell written in standard cell notation. Zinc-zinc ion constitutes the anode half cell. Hydrated copper ion, copper metal constitute the cathode half cell. This again is the half cell in which oxidation occurs. Specifically in this system, zinc is being oxidized to hydrated zinc ion, whereas in the cathode half cell reduction occurs. Specifically for this system, hydrated copper ion is being reduced to copper metal. We talked yesterday about the fact that you can increase E0 cell and E cell significantly for this system if you take and treat the anodic half cell compartment with ammonia solution. Because in so doing, oxidized zinc will now become the zinc ammonia complex ion, because the zinc ammonia complex ion is a whole lot more stable than the zinc water complex ion. So now you'll provide a significant increase in thermodynamic drive for oxidation to occur. Zinc will much more readily oxidize and become the more stable zinc ammonia complex ion. But we also decided, don't add the ammonia to the cathode half cell, because that will convert the copper water complex ion to the copper ammonia complex ion. And for this system, the copper water complex ion is the oxidizer, the stuff that gets reduced. So if you turn this into a more stable ion, you will decrease the thermodynamic drive of the system, because the copper ammonia complex ion, since it's more stable than this, is more difficult to reduce. It's a poorer oxidizer than this. That makes E cell and E0 cell nosedive. Now, specifically for this cell, could we replace the cathode electrode, which is presently a strip of copper, with a strip of silver and maintain cell operation? Imagine we got this system running before us. I decide, just for fun, in this case the fun is your intellectual stimulation. I take away the copper strip, which functions as the cathode electrode, and replace it with a silver strip, and then reconnect. Will the system still operate? Will the system still deliver the same E cell and E0 cell values? E cell will, of course, depend upon the molarities of hydrated copper ion and hydrated zinc ion, respectively, as they appear in the Q part of the Nernst equation. I take away the copper strip, replace it with a silver strip. What if I take away the copper strip, replace it with a platinum strip or a gold strip? Will the cell still operate? Will it still operate at the same E0 cell and E cell values? Yes or no? Knowing full well that I don't give a damn about votes. Unless you vote correctly and defend it. How many say, yes, I can remove the copper functioning as the cathode material, replace it with a strip of silver. Everything still works fine. I got a vote. I got 2 votes. Maybe that's just a half a vote. Now it's a questionable half a vote. Well, what is the functionality of an electrode? What does it do in an electrochemical cell? Well, in the cathode compartment, the cathode electrode material serves 2 purposes. What are the 2 purposes? Well, there's got to be a conductor, because we've got electrons traveling through this system. Is copper a good conductor? Is silver a good conductor? Silver happens to be the best conductor of all metals. Well, maybe you'd like to go home and ask Mom and Dad to replace the copper wiring, which you probably have, with silver wiring. But now you better have armed guards around your home. People probably come in and remove the silver wiring because of the value of silver. The answer to the question, and the other purpose of the cathode electrode is to provide a surface upon which reduction can occur. Remember, as this system runs, or specifically this system, as zinc is oxidized to hydrated zinc ion, zinc atoms lose electrons. The electrons travel through the external circuit. The external circuit allows us to use the electrical energy that's liberated by this redox reaction. And ultimately, after the electrons travel through our meter or our light bulb or whatever, demonstrating the usability of the energy supplied by this system, the electrical energy supplied by the system, then the electrons go, in completing the circuit, over to the cathode material. Like over there. Now, all positive ions naturally travel toward the cathode, right? Because as this system runs, the cathode electrode is continuously enriched with electrons, and they're negative. So all the positive things travel toward it. The positive thing with which we are concerned in this system is hydrated copper ion, which on traveling toward and touching the cathode electrode collect these electrons and wham, become copper atoms. So can I take away this copper strip and put in a silver strip and still have the system operate? Will the silver reduce to hydrated copper ion? Will I create a short circuit by taking away my copper strip and replacing it with a silver strip? Will that create a short circuit? We talked about this last time. Which is the stronger reducer, silver metal or copper metal? If you don't remember, look at the half reaction table. In fact, you'll need to look at the half reaction table as we proceed with this conversation. So you might as well open it right now. Table 2. Chapter 22. Which is the stronger reducer, silver or copper? Copper. So silver's not going to reduce the hydrated copper ion, but silver's an excellent conductor. So now, what will happen if I take away my copper strip, replace it with a silver strip? Is that electrons will now travel to the silver strip. The copper ions will swim over, on touching the silver strip, collect the electrons which are being pumped into the silver strip by the oxidation process taking place in the anode half cell, and become copper atoms. So now I'll be plating copper on silver. Now, if I don't want to contaminate silver with copper, I wouldn't want to do this. But electrochemically, this changes nothing. the system will work just fine. It'll give us the same E value, the same E0 value. Why? Because silver is an excellent conductor, and because silver would not create a short circuit, because silver does not reduce hydrated copper ion. I could do the same thing by replacing copper with gold, copper with platinum. I picked on silver because you know from the information in the half reaction table that copper is a stronger reducer than silver, plus we've already talked about this. Now, let's imagine I leave the copper strip intact. The cathode material is still a copper strip. Now I go over to the anode. In this system, zinc is the anode material. I take away the zinc strip and insert a silver strip. So now I have a silver strip standing in a solution containing hydrated zinc ion and the anion, sulfate ion, whatever it might be. And after making the connection to the wire, I go look at my voltmeter to see what kind of voltage I'm now getting out of the system. What do you think I'm going to read? I will read 0, because now the system shuts down totally. Why does the system now shut down totally? Do you realize that in this electrochemical system, zinc solid is not only the anode, it's the reducer. It's the stuff which is causing copper ions to collect electrons and get reduced. It's the stuff which gets oxidized as this electrochemical system functions. Zinc gets oxidized to hydrated zinc ion. Can silver reduce hydrated copper ion? No. Can silver reduce hydrated zinc ion? Well, if silver can't reduce this, it sure as hell can't reduce this. Because this is a poorer oxidizer than this, right? Because this is the conjugate oxidizer of this reducer, and this reducer is stronger than this reducer. You've got to pull all the puzzle parts together, and then it makes sense. Now, what would happen if instead of the silver strip, I take away the zinc anode material and I put in a strip of aluminum? I take one of my empty beer cans. Empty first, I don't want to throw away the beer. And I mash it into the shape of an electrode. And after having consumed the beer, I'm in an imaginative mood. So I want to see what the hell happens. I'm curious. What the hell is now going to happen when I take away the zinc anode and replace it with aluminum and have the aluminum metal function as the anode? What's going to happen now? Look at the half reaction table. Can aluminum reduce hydrated copper ion spontaneously? You're damn right. Can aluminum reduce hydrated zinc ion spontaneously? The half reaction table provides this information. Which is the stronger reducer? The more reactive metal, aluminum or zinc? Aluminum. So guess what I'm going to do now? Because in order for the electrons to travel through the external circuit, I have to overcome a property of any electrochemical system called resistance. But now the aluminum can be oxidized directly by giving its electrons to hydrated zinc ion. So what will probably happen if I did this thing I talked about, I smashed up my aluminum beer can and turned it into my anode material by taking away the zinc strip and replacing it with the aluminum strip, is I'll probably have a short circuit, because aluminum ion is now touching hydrated zinc ion. And even though hydrated zinc ion is not as strong as oxidizer's hydrated copper ion, I have no resistance battle to fight. Because now the electrons would travel directly from aluminum atoms to hydrated zinc ions, while hydrated zinc ions become zinc atoms on the surface of aluminum. Short circuit. Don't want to do that. And after I would have done this with my beer can and all that, wow, look at that. Now I'm making zinc metal deposit on my aluminum beer can. But E cell and E0 cell would again go put down to nothing, because I wouldn't have any electrons traveling through my external circuit. At least that's my bet what would happen. You think I'll ask questions like this on Friday? You're damn right. Because I want you to be able to tell me that you know how an electrochemical system functions. Now, let's go one step further with this electrode consideration. Look again at Table 2, our table of half reactions. Do you see at a glance that there's quite a number of half reactions listed in this table, which in order to be part of an electrochemical system have to be outfitted with an electrode? Take a look at half reaction 16. Hydrogen functioning as a reducer in the presence of pH 14 hydroxide ion, and in so doing getting oxidized to water. Do I have to put an electrode into that system? Is hydrogen a metal? Hydroxide ion? Water? I got to put an electrode in there. And I got to put an electrode in there which will serve the purpose of completing the circuit and functioning as a good conductor. But I do not want the electrode material to be something which will interfere with the operation of the electrochemical cell I'm trying to build. Like what happened here if we imagine replacing the zinc strip with the aluminum strip. I mean, for example, you think sodium's a good conductor? It's a damn good conductor. You want to wire your home with sodium wires? What the hell are you going to do when it rains? My home just went up in flames. My wires are all on fire. Why is that? Well, you look down the list, you'll see a number of half cells which have got no metal component, not just a solid, not ionic compound. Got to have a metal in there to behave as an electrode. And as I said, or mentioned in passing, platinum, for example, is a commonly used electrode material. It's very durable and very unreactive. Carbon graphite's commonly used as an inexpensive electrode material. Remember when we talked about the properties of carbon graphite versus carbon diamond, and recognized that one of the differences is that carbon graphite's a conductor because of resonance? Maybe we forgot to mention that back then. But solid state materials which have this property of resonance are conductors. These resonance electrons, so to speak, are mobile, even in a solid state. Interesting. Now, take another look at Table 2. And in so doing, I will ask if, for the pages in the notes we are presently considering, discussion of the Nernst equation, and its usage? Did you read about the construction and operation of a pH meter? That's at the top of page 22-23. At least that's where the discussion begins. Now, in looking again at Table 2, our list of half reactions, do you see various and sundry half reactions which could be used to construct a pH meter? If you're going to make a pH meter, you've got to have, in the electrochemical system which you build, a half reaction whose behavior is sensitive to pH, directly so. Now, if we're looking for a half reaction that's directly sensitive to pH, what chemical ingredients do you expect to look for?
Hydroxide.
Hydroxide ion or? Hydronium ion, sure. A whole bunch of half reactions there which have this quality. The most commonly used, I would imagine, is the standard hydrogen electrode. I don't remember the number, but I think it's 29 or something like that. It's the one where the voltage is 0 by definition. The standard voltage is 0 by definition. Is that 29? Is that it? The details of the considerations necessary in regard to constructing a pH meter, the details related to the Nernst equation, are all in the notes. You can read that. Now, let's go forward with this Nernst equation consideration and look at question 22-24, part 1. Take a look at half reactions 19 and 39 in our table 2. We're going to couple these half reactions to make an electrochemical cell to give us usable electrical energy. Half reaction 19 corresponds to the oxidation of copper metal in the presence of hydroxide ion, basic system, and hydrogen sulfide ion. The oxidation product is copper sulfide. Just for curiosity, you folks in 46L, anybody yet in assignment 7? Those of you in assignment 7, have you yet run any reactions and produced copper sulfide? Have you found out that copper sulfide is very stable stuff? I mean, copper sulfide is a solid containing, as the anion component, sulfide ion. A damn strong base. A base stronger than hydroxide ion. But practically speaking, you can't dissolve this sulfide by just hydronium ion attack. You would expect to be able to because of the strong basic nature of sulfide ion. But you can't really effectively dissolve copper sulfide with hydronium ion attack. You'll find out in 46L when you go to assignment 8 that if you want to dissolve very stable sulfides like copper sulfide, and in addition to copper sulfide in assignment 7 you'll manufacture some silver sulfide, which is also very stable stuff. You need a double attack, a potent double attack. This is assignment 8, 46L. You'll need hydronium ion in high concentration and nitrate ion in high concentration. At least this is one way to do it. You remember the hydronium ion nitrate ion combo is a strong oxidizing system? Clearly it's also a strongly acidic system because of the high molarity of hydronium ion. In the half reaction table, or as it follows from conversation we just had, silver metal, copper metal, These are weak reducers. Much weaker reducers than zinc, aluminum, other common metals. But if you place silver metal or copper metal in the presence of a source of sulfide, all of a sudden these very weak reducers become damn strong reducers. Look, for example, at half reaction number 32. Half reaction 32 we've already talked about. It's part and parcel of this Daniell cell. Half reaction 32 shows copper in the presence of water being oxidized to hydrated copper ion. The standard cell potential, half cell potential for that is minus 0.34 volts. I'm just citing this data from the notes, from the table. Well, when you got copper in the presence of hydrogen sulfide ion and hydroxide ion, and now you're oxidizing it to copper sulfide, not hydrated copper ion, look at E0. It's plus 0.76 volts. Ha-ha! Huge difference. Because now you have the powerful thermodynamic drive supporting the oxidation of copper. The powerful thermodynamic drive being the oxidation of copper to this damn stable stuff, copper sulfide, as opposed to that very reactive, strong oxidizer, hydrated copper ion, comparatively speaking. All right, we're going to couple up half reaction 19 with 39. Now look at 39 in the table. And when you're looking at 39, you may as well also look at half reaction 23. You see anything unusual about these half reactions? 23 and 39? What does the information in the table tell you? Information in the table tells you that the voltages listed for these half reactions are not E0 values. They're E values. Do you see that each of these half reactions, 23 and 39, are considered operating at a pH of 7.00? Right? That's what the notes tell you. Is pH 7.00 a standard condition half cell? Is pH 7.00, you got hydronium ion in there at 1 times 10 to the minus 7 molar. Or hydroxide ion is 1 times 10 to the minus 7 molar. Either one. Is that standard condition hydronium ion or hydroxide ion? What's standard condition? 1 molar. Hey. So if you want a hydroxide ion or hydronium ion containing half cell to be operating at standard conditions, you got to have hydronium ion 1 molar or hydroxide ion 1 molar. You got to have pH 0 or pH 14. Otherwise it's not standard state. So number 39, given that we're considering oxygen functioning as an oxidizer in the presence of water to make hydroxide ion at pH 7 is not a standard half cell. That means the E value tabulated in the notes is not an E0 value. Well, if I want to get E0 for this electrochemical system after I couple these half cells, I need an E0 value over here. What is it? Now, if you read question 24 in the notes, it will tell you in calculating E0 for this cell, 2 values are possible. 2 values. It won't change the operating potential for the cell. We'll explain that in just a moment. But I want you to tell me why it's possible that this electrochemical cell has 2 possible E0 values for the net cell. Why is that? Look at the table. You looking at the table? You see 39 as it is stated in the notes in the table. It's talking about hydronium ion at pH 7 or hydroxide ion at pH 7. Those are the same system. if I consider this chemically to be hydroniumine at pH 7, what E0 value do I attach to half reaction 39? Tell me the number, the E0 value. The value for E0. It's in the table. Just tell me the value. Now repeat. If you cannot read this table and understand it, you got big trouble this Friday. I'm listening for a value. Plus 0.40 volts or plus 1.23 volts? Which one do you want? Where'd I get these numbers? Is it magic? Evil magic? Created by the crazy chemistry guy? Plus 0.40 volts. I call your attention to half reaction 35. You looking at half reaction 35? If I take half reaction 35 and write it in the opposite direction, just like when I took half reaction 39 to play the coupling game, I wrote it in the opposite direction. Okay. Do you see the similarity in the composition, chemical composition of half reactions 35 and 39? Does 39 reverse show oxygen functioning as an oxidizer? Does 35 reverse show oxygen functioning as an oxidizer? At pH 14. So now we got oxygen functioning as an oxidizer under standard state conditions. How about that? Now where did I get this plus 1.23 volts? How about 41? Now I got oxygen functioning as an oxidizer at pH 0. Tell me, from these considerations, is oxygen a better oxidizer under acidic conditions or basic conditions? Acidic, much better. In general, if you want to increase the oxidizing power of an oxidizing system, make the system acidic or basic? Acidic. If you want to increase the reducing power of a reducing system, make the system acidic or basic? Basic. That's right. I don't know if you've noticed this about food chemistry, but acidic foods, they last a long time. Spaghetti sauce, made with tomatoes, fairly acidic. You can uncap a bottle of spaghetti sauce, take out what you want, recap it, put it in the refrigerator. It lasts a long time. That's acidic. It's a good oxidizing system. Little buggies get in there and they get murdered by oxidation. But basic systems are good reducers. I don't know specifically how I tie that in. Oh, what happens now is that the basic food, by reducing atmospheric oxygen, will cause oxidation of the basic food and ruin it. Basic foods don't last long. Chemistry. We just talked about it right now. Now, just because in my notes, to go further with this, I use this value. I'll do it again. But you could use either value. It will not change the E cell value that you will calculate. So when we now go further with this, by application of the Nernst equation to get E cell, I would tell you for your own benefit, put in a 1.23 volt value, and then for the concentration and partial pressure conditions cited, calculate E cell. Because you should get exactly the same value as we shall now get by using this as the E0 cell potential. Here's the net cell reaction. I've written for this net cell reaction E cell over here. I mean the Nernst equation over here. We now know what to put in for question mark. And above that I'll put or question mark. Because if you put in the plus 1.23 volts value, you'll get a different E0. I'll let you do the arithmetic. What's N? Want to use the Nernst equation, we've got to know the value for N, and the value for N comes exclusively from the cell reaction. It's the only place you can get N. Oh, we got the cell reaction on the board. What's N? What is it? 4. That's it. Nothing fancy about this. If I oxidize 2 moles of copper to 2 moles of copper sulfide, I've observed a total change in increase of oxidation state of plus 4. Same for a mole of oxygen, becoming 2 moles of minus 2 oxidation state oxygen. Minus 4. N is 4. If I go through this thing and double the coefficients, what's N? If I go through this and double these coefficients, what's N? What is it? 8. If I triple the coefficients, 12. If I divide the coefficients by 2, then N is 2. Just pay attention to total change in oxidation state for the stuff that's oxidized or for the stuff that's reduced, because it's the same number. Now then, please take a look at the top of page 2218. In the event that you've not yet looked at this information, the discussion at the top of page 2218 is reminding you again about something we've talked about. To operate an electrochemical cell and have it deliver usable electrical energy, you've got to physically separate oxidation from reduction. In many cases, that requires separating all the chemical components of the anode half cell from the cathode half cell. Because if you don't do that, you got a short circuit. That's what this discussion at the top, page 2218, is about. So when you write the Nernst equation for an operating electrochemical cell, like we have written here for this cell, hydroxide ion concentration to the fourth power up top corresponds to hydroxide ion in which half cell, anode or cathode? Here's the half reaction. This anodic hydroxide ion or cathodic hydroxide ion? And I'm going to ask about this hydroxide ion. Because whichever one we identify as to be the cathodic hydroxide ion, then the other one's the anodic hydroxide ion. The top hydroxide ion is in which half cell? Cathode or anode? Cathode. Well then, by default, bottom hydroxide ion, denominator hydroxide ion is anode. Is this right? Do you all agree with this? You better. See the half cells? Number 19 corresponds to oxidation. So 19 shows the chemistry that's occurring in the anode. 39 corresponds to reduction of oxygen. So the chemistry shown by 39 is taking place in the cathode. And for 39, 4 moles hydroxide ion is product. Product, that means in the numerator. So that's cathodic hydroxide ion up top, correspondingly anodic hydroxide ion in the denominator. So recognize now, when you do Nernst equation calculations on an operating electrochemical cell, you can't cancel these hydroxide ion molarities with each other. You can't draw a line through this and a line through this and say the whole thing is net hydroxide ion molarity squared up top, unless these molarities compare how? They're equal. Then you can do it. But if they're not equal, you can't do this. Because these hydroxide ions are physically separated from each other. At least they may well be, depending upon the electrochemical cell that is in operation. Now, I was going to do this when we talked the other day about the lead cell in the car battery. But as it turns out, hydronium ion and hydrogen sulfate ion in the lead car battery is constant throughout the system. So you don't have to pay attention to in applying Nernst to the lead battery. You don't have to pay attention to hydrogen sulfate ion numerator, hydrogen sulfate ion denominator, and treat them as separate, because they're not for the lead cell. You can look that up on the web if you want to. That's how I found out about it. Now then, I've drawn a picture of this over here. Here's hydroxide ion in the anode half cell. Here's hydroxide ion in the cathode half cell for this particular electrochemical cell where copper is the anode material and getting oxidized. Notice that for this metal strip I've got immersed in the cathodic solution system. And in the cathodic system, you're also going to have a cylinder over here. There's a meter. I could wheel out a gas cylinder from the back. You've all seen gas cylinders. What do you think is in this gas cylinder?
Gas.
What? What's in this gas cylinder? I'm looking at operating half cell 39. What's in this gas cylinder? Oxygen! That's got to be bubbled in here. It's probably going to be bubbled directly on the surface of this thing. What do we want this thing to be? This electrode material. Question mark. Piece of sodium, damn good conductor. Look at that system. That would be fun. Put a piece of sodium in contact with oxygen bubbled in the presence of water. Kawoosh! Oh, my cell, I wrecked it. You wrecked yourself too on that. No, you got to put something in there that's a good conductor, but which will not react chemically with any components of the system. My bet is it's going to be a strip of platinum. It might be a copper graphite stick. So, all right, electrode is perhaps PT. Carbon graphite, silver bar would probably work for this, as long as that silver bar doesn't touch this sulfide ion stuff. Now, you can do the arithmetic. For this system, I get E cell is 1.08 volts. For the conditions stipulated. Notice the pH of 14.30. Please do not be perplexed by this pH. Just recognize that pH of 14.30 corresponds to a hydroxide ion molarity that compares how to 1 molar. It's a little bigger. It's 2 molar. If I give you a negative pH, what's that tell you? Now you're dealing with a hydronium ion concentration that is greater than 1 molar. That's all. Now remember what I said. If you use the plus 1.23 voltage value and get a different E0 cell, when you calculate E cell, you'll still get this number if you do the arithmetic properly. Now, part 2 of question 24 is to say something that's parallel to what we talked about the Daniell cell when I gave you the bottle of 6 molar ammonia. And I said, what do you want to do with 6 molar ammonia to up E cell, E0 cell? Well, here I'm going to give you a bottle of 1 molar HCl. Can you operate on this system so as to make E cell as well as E0 cell go up by usage of 1 molar HCl? Well, back to the choices. I can take the 1 molar HCl and put it in the anode compartment. I can take the 1 molar HCl, put it in the cathode compartment. I can take the 1 molar HCl, put it in both compartments, or I can say any treatment I apply with 1 molar HCl is going to make E cell and E0 cell come down. 4 choices. of which only one is correct. What is your choice? What are you going to do with this 1 molar HCl? How many vote I'm not going to do anything with it? How many vote I'm going to treat both cells? Both half cells. How many vote I will treat the cathode half cell exclusively? How many vote I will treat the anode half cell exclusively? We got 1 right vote. You remember when we looked at these E0 values, possible E0 values for the oxygen-containing half cell? Under what pH conditions is oxygen the better oxidizer? High pH or low pH? High pH or low pH? Oxygen as an oxidizer. Low pH. Well then, damn it, I'm going to take this 1 molar HCl and I'm going to put it in my cathode compartment. Because when I do that, I now will have oxygen being oxidized in the presence of water to make hydronium ion. The E0 value will be plus 1.323 volts. And the pH will be, if I put in enough of this 1 molar HCl, I can make the pH effectively 0. I'm going to make this a much stronger oxidizing system, and in so doing, E cell and E0 cell are both going up. Now remember, we'd have grossly different values. For what we're now going to have in the numerator of our Nernst equation. Now I want to put that hydronium ion in my anode half cell. Because if I put hydronium ion in my anode half cell, I'm going to convert this stuff to H2S. I'm going to convert this stuff to water. Now look at the half reactions. Is copper a stronger reducer under basic conditions or acidic conditions? We've already answered this, but now put it to use. If I oxidize copper in the presence of H2S and make copper sulfide, versus what we have here, we're oxidizing copper in the presence of hydrogen sulfide ion, not H2S, and making copper sulfide. Which is the better reducing system? Under what conditions is copper the stronger reducer? When it's oxidized by H2S or when it's oxidized by HS minus in the presence of hydroxide ion? Hey, this is plus 0.76 volts. What's E0 for this one? Plus 0.134 volts. Is that right? Because now I'm going to make, beside that, I'm going to make hydronium ion. Hey, we just talked about this a moment ago. In general, a reducer is best under basic conditions. And in this case, the reducer is copper. And as copper functions as the reducer, it's becoming oxidized to copper sulfide. And if nothing else, from an acid-base standpoint, you know damn well this stuff is more stable in basic solution than it is in acidic solution. This has got sulfide ion in its composition. That's a potent base. Now this stuff is stable in the presence of hydronium ion, but certainly it's more stable in the presence of hydroxide ion and HS minus, because these have no tendency to attack this from an acid-base standpoint, but hydronium ion has a potent tendency to attack this. It's an application of what we did in chapter 18 again. I'm telling you, that's when this stuff makes sense, when you put it together. That's the hard part. I know, I'm sympathetic with you. But that's why I'm trying to do what I can to help you recognize how to put it together. Okay? Now, question 25. Look again at the half reaction table. I want you to tell me which half cells you have to couple. If your task is to calculate the solubility product constant for ferrous hydroxide, iron in the +2 oxidation state hydroxide, which half cells do you have to couple? I want the numbers and I'll write them down here. Now, do you realize, I hope, and in answering this question, you got to remember what KSP corresponds to, how KSP is defined? Is the salt of limited solubility in the equilibrium reaction for which K is equal to KSP. Is the salt of limited solubility a reactant or product? What is it? Reactant or product? And some of this stuff you got to remember. Reactant or product? What is it? Don't remember? And then we got a problem. I mean, if I talk about KSP and you don't know the answer to the question which I just posed, how the hell can you understand what's going on? Do we have the salt on the left as a reactant in equilibrium with its component ions? Or do we have the component ions as reactants in equilibrium with its salt of limited solubility? What kind of numbers have we observed for KSPs? Are they big numbers or small numbers? Damn small. We're talking about materials which aren't very soluble. So do you think these materials, when they dissolve, are going to contribute to a large concentration of the component ions or a tiny concentration? Tiny. So where's that damn salt? Reactant or product? Reactant, you betcha. If you think about it, it comes. And if you don't think, it's horrid. So we're looking for the half cells, which on coupling will allow us to calculate the K value for the equilibrium established by this reaction dissolving in water and giving its component ions to the resulting water solution. All right, what are the component ions of this stuff? More chemistry. What ions react with each other to make this stuff? And at the same time are recognized as the component ions of this stuff. What are they? I heard something, but it was too faint.
Iron 2 plus hydroxide.
Iron 2 plus what?
Hydroxide.
I don't know what that is. This is iron 2 plus hydroxide. That's not an ion.
Iron 2 plus and hydroxide.
Iron 2 plus. Tell me the complete formula. I accept your statement that this iron ion is in the +2 oxidation state. But I want to know the complete formula for this ion.
OH2.
Ha ha ha. Now we're getting there. Remember, these multi-charged metal ions likely form hexahydrates. Here's an example of such. You'll see this ion listed in our table. And this ion reacts with what? You told me. What is it? Hydroxide ion. How many? 2 moles hydroxide ion. Now, is this an equation? Well, it doesn't balance, so it's not an equation. What's missing? Water where? Left or right? How many waters? How about that? Wonderful. Now tell me which half cells to couple in order to calculate the equilibrium constant for this reaction, which by definition is KSP for this stuff. I want the numbers for these half cells. I heard 15. Fifteen's one of them.
22.
Has 15 got this hydrated ferrous hydroxide hydrated ferrous hydroxide in it? Well, then I sure as heck got to have that one. That's 15. What's the other one?
22.
22 is a winner. Now, in coupling 15 and 22, to answer the question, calculate KSP for ferrous hydroxide. Which one gets reversed? 15 or 22? 15 gets reversed. So we're going to write this down. What's N? Log KSP. It's going to be the molarity of this times the molarity of this squared. Because by definition, that gives us KSP for this stuff. All right? Now, one more puzzle part. We want to calculate KSP. Here's what we want to calculate. What's E0? You're looking at it. Negative 0.44. Any seconds for that? I didn't write it down. You second? Third? Fourth? Good. We'll take that. What's E cell? What's E cell? How much is it? Say again louder, I heard it. 0, damn it. This thing's at equilibrium. Not going anyplace. That's the chemistry of the system. When Q is equal to K, isn't this the case where Q is equal to K? We're at equilibrium. The change in free energy for the system is zilch. This baby isn't doing anything from a net change standpoint. So now you got one equation and one unknown. Calculate. If you do the arithmetic, you should get 1.2 times 10 to the minus 15. Of course, that's presuming I did the arithmetic right. All right? Now, you'll finish the stuff for chapter 22 tomorrow in discussion class. Be there. But let's take a look at one more, and then we'll quit for today. I want you to revisit half reactions 23 and 39, which we have already recognized to be non-standard half reactions. They have E values tabulated, not E0 values. Well, my question to you is, where do these E values come from? So I wrote it up here. How do we calculate E for these non-standard half cells? Now I'm listening for suggestions. Nernst equation. E half cell equals E0 half cell minus 0.059 V over N times log of Q. All right, let's pick on this one. You see this one in the half fraction table? Hydrogen being oxidized in the presence of water at pH 7 to become hydronium ion. What is the E value cited? What's it say in the table? E half cell equals 0.41 volts. All right? What's N? 2 electrons. Says 2 there. The log term is hydronium ion squared over partial pressure of hydrogen gas, which will be 1 atmosphere. That's not standard, I have to tell you. But so far, the only non-standard component of this is the hydronium ion concentration. So the remaining part is, what's E0 cell? E0 half cell, pardon me. All you got to do is to look at this half cell reaction and imagine it to be conducted under standard state conditions. And in so doing, you will find out that for this half cell, at standard state conditions, E0 is how much? How much? 0! It's a standard hydrogen electrode. And this is 1.0 times 10 to the minus 7 quantity squared. So this becomes 1 times 10 to the minus 14. What's the log of 1.0 times 10 to the minus 14? What is it? It's minus 14. So the minus signs go away. So 2 in the 14. 7. 7 times 0.6, roughly. 0.42? Of course, it's only 5.9. Done. You finish up chapter 22 tomorrow. Be there.